This is the course Mechanical Vibrations. Today we will talk about free vibrations with viscous damping. My name is Carmen Muller-Karger, and some figures and content are adapted from our textbook, The Mechanical Vibration from Brown. This represents chapter 2, and we will talk about free vibrations of single degree of freedom systems. The learning objective of these presentations are the following. We will solve a spring mass damper system for different types of free vibration response depending on the amount of damping. And we will learn how to compute the natural frequency, the damping ratio, and the damped frequency of vibration. If we have a system that is composed by a mass, a spring, and a damper, and we measure the x or the motion respect to its equilibrium position, we will have this free body diagram. You see that we are ignoring the weight because the weight will cancel out with the static deflation of the spring. So we have the force of the spring, we have the force of the damper, and then we have the motion of our system. The viscous damped force is proportional to the velocity and is the relative velocity between the two ends of the damper. And it can be expressed as negative, the coefficient of damper, times the velocity between the two ends of the damper. Here we can see a figure how a damper looks like. So we have two ends, we have a fluid within the cylinder, and we have a piston that compresses that fluid. That force will not depend on the position of the piston, but upon the velocity of the piston. C is the damping constant or coefficient of viscous damping, and the negative signs indicates that the damping force is always opposite to the direction of the velocity. Now, if we apply the second Newton's law to our free body diagram, right here, I call x the vertical direction, that's where our variable is called, and then we have the static deflection, will cancel out with the weight, that's where we didn't draw the weight, right here, and then if x is measured from the static equilibrium position, then we have this equation of motion, where we have the term mass times the acceleration of the system, c, that is the constant of the damper, times the velocity, plus k, which is the constant of the spring, times the displacement of that mass. And that's equals to 0. The solution of this second order differential equation can be found by assuming that the function is a constant times exponential s times t. If we derive this expression, we will get sc exponential st, and if we derive again, we get s squared c e to the st. If we substitute these three terms in our equation of motion, we get this expression right here. Since this term cannot be 0 because c is not 0 and e to the st cannot be 0 either, we have to make this term equals to 0. So this is what it represents, an eigenvalue problem or eigenvalue of the equation. So we will solve this quadratic equation for s to get the solution of our differential equation. So the characteristic equation is this one right here. This is a quadratic equation, therefore these are the two possible solutions. And if we expand those two, these are the two possible solutions. And if we introduce that into our equation, we get that the solution becomes c1 e to the s1t, s1 being this term, plus c2 e to the s2, and s2 being this term. So if we substitute those two terms, we get that the solution respect to time of our differential equation has this form. Now that we have our two solutions, let's introduce some parameters. We already have introduced the concept of natural frequency. Natural frequency of the system will be equals to the square root of the constant of the spring divided by the mass of the system. Now we have another parameter that is called critical damping constant. We will define the critical damping constant as 2 square root of km, or, which is the same, 2m omega n of the system. And this is a very important definition, which is the damping ratio. The damping ratio will be the constant of the damper of the system divided by this critical damping. So it will be C divided by 2 square root of km, or C divided by 2 omega n. The damping ratio is a dimensionless coefficient that relates the constant of the damper and the constant of the spring and the mass. This is a very important concept, and just imagine if you put a damper that you use for a truck, which is a very heavy vehicle, into a car, will that damper work? And you probably say, no, that will not work, because the mass of the car is much less than the mass of the truck. So you have to put a smaller damper for a smaller mass. So the behavior of the system will not only depend upon the constant of the damper, but will depend on a relation between the constant of the damper, the constant of the spring, and the mass of the system. Now, let's try to get our equation of motion in a form that will include the damping ratio and the natural frequency. So I will divide all the equation by the mass, and if you see, and I manipulate a little bit that ratio, I will get that I can say that the ratio between C over n, I can write it in terms of 2 zeta being the damping ratio, times omega n. And I can write my same equation of motion in this form, where this is the acceleration, 2 zeta omega n, the velocity, plus omega n squared times the displacement equals to 0. And if I do the same for the two solutions and I substitute my parameters into this solution, I will get that the two solutions can be written as negative zeta omega n plus or minus omega n square root of zeta squared minus 1. And then the solutions that I had before can be written as C1 e to the S1, which is this one right here, with a plus, and plus C2 e to the S2. So this represents also the solution to my differential equation. Now, let's see the types of solutions depending on the value of zeta. We have 4 different solutions. When we have no damping, so the constant of the damper is equals to 0 because we have no damping in our system. As you see, these first terms become 0 and the inside of the root becomes a complex number, I. So my two solutions are imaginary solutions. There is no real part in the solution, and we have plus or minus, and this solution is oscillatory. In the case that we have zeta less than 1, we can flip these two values, and we see that this becomes the imaginary part of the solution, and this is also oscillatory. When we have zeta equals to 1, the second terms become 0 and both solutions become real and are equal. And finally, when we have zeta greater than 1, we have the solution as it is, and these are two real solutions, and the response is not oscillatory. For the first case where we have undamped system with zeta equals to 0, my equation of motion becomes the mass times the acceleration plus the constant of the spring times the displacement equals to 0. We do not have the terms of velocity, and the values of the roots are two imaginary roots, which are plus or minus omega n I. the solution becomes then C1 times e to the first solution plus C2 e to the second solution. If I apply the Euler formula, we can expand these exponentials in terms of sine and cosines in this way, right? And then if we put together the cosine and the sine, we see that the terms that goes with the sine is the imaginary value. But C1 and C2 are also complex numbers, so we can write them in terms of C plus di and C minus di, because those two constants are complex and conjugated. Now, if we name A C1 plus C2 and B C1 minus C2, the solution can be written in terms of a sum of cosine and sine. We can also write it in terms of a single cosine with a phase angle. We learned that in a previous presentation, where A relates to x sub 0 as x sub 0 cosine of these phase angles, and B is x sub 0 sine of that phase angle. And therefore, x sub 0 will be the square root of A squared plus B squared, and this is how we define the phase angle. To find the values of A and B, we need to get them as a function of the initial conditions to the system. Remember that we are studying free vibrations, which is a consequence of giving a initial displacement or initial velocity to the system. If we get this expression right here and substitute times equals to 0, we get this value right here. If we derive this expression, we get the velocity, so velocity to 0, and we get this expression right here. If we solve these two equations, we get a value of A that is equals to the initial displacement, and B will be equals to the initial velocity divided by omega n. And remember, we can always relate the expression for a single cosine value. The amplitude will be the square root of A squared B squared, therefore I get this expression. And the phase angle will be the inverse tangent of V sub 0 x sub 0 omega n. And this is a system that oscillates at its natural frequency. Let's see a graph of this curve, and as you see, this is an oscillatory motion. The phase angle is this one right here. The amplitude remains constant. This is the amplitude, and this is this value right here. The period is 2 pi over omega n because the system oscillates at its natural frequency. And this will represent the initial displacement of the system. This represents the initial velocity of the system. And as I said, the system oscillates to its natural frequency. The second case is when we have an underdamped system. We have damping because we have a system composed with a constant of the spring, constant of the damper, and a mass. And the relation between the damper, the spring, and the mass give us a value of theta less than 1. This is the equation of motion, and we said that these are the solutions, and the solution will be complex and conjugate. If we define the damped frequency as omega n square root of 1 minus theta squared, this is this value right here of the imaginary part of the solution. And then the solution becomes x sub d c to the e to the s1. And as you see, I substituted this part over here by omega d. And here we have s2. If we expand using the Euler formula, we get this expression right here for the first part and this expression right here for the second. If I group together C1 and C2, which are the ones that multiply the cosine, and C1 minus C2, which multiply the sine of omega d, and as I did before for the undamped system, these C1 and C2 are also complex constants. So, and I substitute C1 plus C2 by A and C1 minus C2 by B. And A and B are not complex because this term here becomes I times I, which is a -1. The solution can be written in terms of a cosine and a sine function like that, or a single cosine function with a phase angle, very similar to the previous case. Now, to find the values of A and B, again, we have to relate those constants with the initial conditions that we applied to the system. That will be an initial displacement and an initial velocity. We substitute the initial displacement when time is equals to 0, and then time is equals to 0 here. And you know that sine of 0 is 0, so only this term is valid, and cosine of 0 is 1. Therefore, from this equation, we get that A is equals to x sub 0. Then we derive this expression, which is a little bit long because this is two functions that are a function of time. Therefore, we have to apply the rule that it will be the derivative of the first and the second plus first and the derivative of the second in each case. So we have 4 terms. And then we substitute by 0, and then we can find B with these equations right here because we already have A. Therefore, we have that the system responds to this expression right here, where remember that omega d is a function of omega n as omega n square root of 1 minus zeta squared. And as you see, the system oscillates not to the natural frequency but to the damped frequency. We can also write the solution in terms of a single cosine function, which will be this one right here. And again, we can relate this amplitude to A and B as the square root of A squared plus B squared. And since A and B have this value, that's how we can write x sub 0. And again, the phase angle will be the inverse tangent of B over A. And if we graph this expression, we'll have this form. As you see here, the amplitude is not constant. It diminishes with time because the system is losing energy. That energy can be transforming into heat. Here we have that the internal function is our solution, and these are what are called the evolvent. We represent the amplitude of that cosine function, and this is the amplitude of my cosine function. So this system does not oscillate to the natural frequency, but it oscillates to the damped frequency. And these two represent the initial displacement, and the slope represent the initial velocity. The logarithmic decrement represents the rate at which the amplitude of the free damping vibration decreases. So we can express the amplitude of the function at a specific time t1 with x evaluated at t1, and another one subsequent amplitude at t2. If we know that between t1 and t2 we have one period, we can say that t2 is equals to t1 plus the period. And we know that the function evaluated at two different times separated by a period are equal. And we also know that the period of the function is 2 pi over the damped frequency, and the damped frequency is omega n square root of 1 minus zeta squared. So if we divide these two expressions, and we know that we can, this exponent, which will be negative zeta omega n t2, we divided t2 is equals to t1 plus the period, we can separate those two exponentials. And we see that this cancels with this cancels with that, the cosine cancel because they are equal, and we end up with this term over here. Since it's negative, we can put it in the numerator, and it will become this exponential, And if we take logarithm in both sides of the equation, we get this expression. We can cancel out the natural frequency, and then we get what is called the logarithmic decrement, which is dimensionless quantity and is another form to measure the damping of the system. So this is the logarithmic decrement, and we can solve for zeta in terms of the logarithmic decrement. We can also find the two displacements separated by any number of cycles. Between T1 and T2 there is one cycle, between T1 and T3 will be two cycles, so between T1 and Tn plus 1 will be n cycles. So Tn plus 1 is T1 plus n T sub d, which is the period. The cosine, the function evaluated at those two times will be equal. And we can do a similar analysis that we did before. Here, when we have the logarithm of x T1 divided by x Tn plus 1, is that we have this expression multiplied by n. So when we do not use two consecutive periods but separated by n amount of periods, then we can calculate the logarithmic decrement by as 1 over n logarithm of the two displacement, and it will be equals to the same expression. And in this case, we also can solve for zeta in terms of the logarithmic decrement. Since this is a very important concept, let's do an example. We have the motion of a system right here, which we could have obtained by reading the response of the system with an oscilloscope. And then if we see, we have the displacement at a specific time 1 and the displacement at another time. The logarithmic decrement will be the logarithm of the first amplitude divided by the second amplitude. This is 2.8252 divided by 0.634. And this gives us a value of 1.488. We can also use two non-consecutive displacements, which will be, for example, the first one and the third one. And since there are two cycles, we have to divide by 2. We get a similar value. We can solve for zeta in terms of the logarithmic decrement, and we get 0.23 as the damping ratio. Remember the definitions of zeta, which is the damper coefficient divided by the critical damping, and the critical damping is 2 square root of k of m, or 2m omega n, and also the damped frequency, which is 2 pi over the period, which is this one right here, right? And the damped frequency is also omega n square root of 1 minus zeta square. We can also then, reading the period in the graph, calculate the damped frequency, and with the damped frequency we can get the natural frequency. That means that having the response of a system allows us to calculate the damping characteristics and the natural frequency of the system. We can also write the logarithmic decrements in terms of the damper coefficient and the mass, like that. And for very small values of the damping ratio, we can see that this becomes 2 pi zeta. So this is a proportional expression. So as you see here, for small values of zeta, we can say that this is a linear, but as soon as the values of zeta increases, these become non-linear, and then we have to use the expressions that we used for our example in the previous slide. Here we compare the undamped system, which has an amplitude that is constant, and this is the expression for the response of an undamped system, with the underdamped system for zeta less than 1, in which case the amplitude is multiplied by an exponential, and therefore the amplitude diminishes with time and eventually goes to 0. Case 3 is when we have critically damped systems. The equation of motion is the same as in the previous case, but the values of the roots of our characteristic polynomials are real and equal. Since both roots are equal, then we have the first term will be a constant e to the minus omega t, and the second will be bt e to the minus omega nt. And to find the constants a and b, we have to apply our initial conditions from displacement and velocity. So we derive this expression to find velocity. In terms of the displacement, we are able to find a, and in terms of the velocity, we are able to find b. And the response becomes this expression right here. If we graph this response, we see that this is a non-oscillatory response, so we don't have any oscillations in the system. In the contrary, the response goes as fast as possible to the equilibrium position, and the response is equals to 0. If we compare this graph to the two previous ones, in the case of undamped system, we had constant amplitude. In the case of undamped system, we have theta -1. We had a curve that diminished with time in an exponential form. And here we have this critical damped system where the damping ratio is equals to 1. And as you see here, we have this curve that goes to 0 very quickly. The last case is an overdamped system where theta is greater than 1. The equation of motion is the same as the two previous cases, and the values of the roots are real and different. Again, then we have that the response will be a e to the s1, which is this one right here, plus b e to s2t. To find a and b, we apply the initial condition x sub 0 and b sub 0, and those are the terms that we get for the constants a and b for our response. The motion represented is aperiodic, is not oscillatory, and it diminished in time to 0, but much slower than the critical damped system. If we graph this expression, it looks something like that. So we have the slope at the beginning will represent the velocity. This is initial displacement, and it will go to 0 and with an exponential, but much slower than the critical damped system. If we compare here the four cases, the first one that we analyzed is the undamped system, where the amplitude remains constant and the system vibrates to its natural frequency. Then we have the underdamped system, where theta is less than 1 and the system vibrates to the undamped frequency, and the amplitude of the motion diminished with an exponential. Then we have the critical damped system, which is the fastest way to get to the equilibrium position. And finally, we have the overdamped system, which the response is an exponential, but it goes to the equilibrium position much slower than the critical damped system. In the case of critical damp and overdamped system, we do not have an overshoot of the response. Here, as you see in the underdamped system, the response goes up and down. So this is what is called the overshoot. We can calculate the energy dissipated in a viscous damped system, and the rate of change of energy with time is given by this expression, which is force times velocity. Force will be the force of the damper, which is the constant of the dampers and the velocity, and times the velocity. But the velocity is the derivative of the displacement respect to time, and this term is squared. In the case of the damped system, we know that the response is oscillatory. So let's do the simplification and consider that it is a harmonic motion, so we can write it as an amplitude sine of the damped frequency time. And then if we pass this differential of time to the other side of the equation and we integrate in one cycle, we have that this is negative the damper constant times the derivative of the displacement, which is this one, which is x omega d cosine of omega dt, all that square. This cosine of omega dt square can be integrated using the trigonometric identity of sum of angles, and we can convert that to the integral of 1 plus cosine of 2 omega dt divided by 2, and then we have the integral of 1/2 dt t, which is this one right here, and the integral of the cosine. The integral of this term will be omega dt evaluating 0 to 2 pi, and the integral of cosine of the 2 omega dt will be 1/2 sine of 2 omega dt t evaluating 0 to pi. Finally, the energy dissipated can be written in terms of pi times the constant of the damper times omega d, which is the damped frequency, times the maximum amplitude squared. So we said that this expression shows that the energy dissipated is proportional to the square of the amplitude and the damped frequency. If we like to calculate the energy loss in each cycle, we can compute it dividing this energy dissipated by the maximum kinetic energy or the maximum potential energy. Since the velocity is given by the derivative of the expression, the harmonic motion, we have omega d cosine of omega t. The maximum kinetic energy will be 1/2 mass the maximum velocity, which is this amplitude over here, square. We substitute that. We divide the energy loss divided by the maximum energy in a cycle, and then we have this expression right here. Introduce the substitution of C over M as 2 zeta omega n and the definition of damped frequency into our expression, and then we get that the energy loss per cycle has this expression. For small values of zeta, we have that the energy loss per cycle can be written as 4 pi zeta or 2 the logarithmic decrement. And this term here is called specific damping capacity. This represents the last slide of this presentation, and here we have all the formulas and graphs presented in this presentation. We introduced the concept of natural frequency, damping ratio. We will measure the motion respect to the equilibrium position, and the static deflection of the spring is the weight divided by the constant of the spring. The governing equation, we can find the equivalent mass, the equivalent constant of the damper, and the equivalent constant of the spring. We have done that in previous presentations. We can also write the equation of motion with respect to the damping ratio and the natural frequency, and we will have this form. The total response of the system will be the homogeneous response and the particular response. When we have no force applied, we have free vibration, and the total response will be equal to the homogeneous response. So all those responses for free vibration represent the homogeneous response to the system. The first case was the undamped system, where we have no damping. Therefore, the damping ratio is equal to 0. And the response is a harmonic function where the amplitude remains constant and the system vibrates to its natural frequency. Then we have the underdamped system where zeta is less than 1, and we found that the response is also an harmonic force, but the amplitude diminished over time as with an exponential, which we call an Overdamped. The system vibrates to its damped frequency, and we had the concept of logarithmic decrement, which is a measure on how the amplitudes diminish over time. And also it measures the damping of the system. We also studied the critical damped system when zeta is equals to 1 and the response is non-oscillatory and is a response that fastest gets to the system to its equilibrium position. And then we have the overdamped system, which this is the response, and this is also a non-oscillatory system, but the response is much slower than the critical damped system. And finally, we studied the dissipated energy for viscous damped system, and this is what is called the specific damping capacity.